¿El futuro? Despierta. Bienvenido al Congreso Futuro. Despierta, conéctate, participa.
Well, thank you very much. It's quite an honor to be and a pleasure to be here. So let me begin and talk about whether we are going to adapt to climate change. And so before I really talk about that, I need to tell you about some of the responses to climate change. There are two types. One is called mitigation. That is, you take action to lessen the chance that bad things will happen. For example, you decrease global carbon emissions. You stop deforestation and you reforest. Those are mitigation steps. Adaptation is, well, we know it's changing, so you can modify the infrastructure to be more resistant to climate change, severe downpours, rising sea levels, things of that nature. But really the first step in adaptation and mitigation is to understand the risks. It's as if, well, the first step if you are not feeling well is you go to a doctor and you get a diagnosis and then a prognosis. If you do not go to the doctor, you're not properly adapting to a new condition. What's the first thing is understand the risks. So there's a first law of holes. If you find yourself in a hole, stop digging. Now, people might say, hole? What hole? We're not in a hole. So the question is the climate changing? This is the record of the temperature from 1860 to 2014, and it appears the average land and sea temperature is rising, and so the climate, at least the temperature of the Earth in this period, seems to be changing. However, if you look at the last 12, 15 years, you will notice that the temperature has not increased that much. And indeed, if you look over this period of time, it also has not increased that much. And in Washington, D.C., over the last 6 years, a lot of people were asking this question. There's a temperature plateau. And where is the temperature going? If the climate scientists were so smart, they should have predicted this would have happened. They didn't. They predicted it will increase. So there's a reaction to that. And the reaction is, well, this is proof that the climate models can't be trusted. And furthermore, if they cannot be trusted, why should we do anything about it? Because the risks, their estimate of the risks, cannot be trusted. So let me try to tell you why this may be wrong because of marching science. But let me shift gears and go to a time in the summer of 2010. The United States, BP, had a big oil spill. It was an oil 1 mile deep in the Gulf of Mexico. I spent several months helping BP stop this leak. And I noticed something. The surface temperature of the Gulf of Mexico during that summer was roughly 30 degrees centigrade. It was warm bathtub water. 1 mile deep, 1 degree above zero, does not change year-round. 1 degree above freezing, right? The bottom of the ocean is cold, and this isn't really the bottom of the ocean. This is only 1 kilometer. So what this means is it takes a while for the heat and the surface of the ocean and the land to actually warm up the ocean. And so let's see what about. Can we measure this? And so these are called Argo floats. They are dropped from airplanes, and they measure the temperature and salinity at the surface of the ocean. They go down, they measure it again, they go down, they go down. They go down, in this experiment, down 2 kilometers. They come back up, and then they radio back the data to a data collection center. Well, 1 float is not enough. You need to cover some fraction of the ocean. That's how many floats there are. And so with this many floats going up and down 2 kilometers, now going up and down 6 kilometers in the newer experiment, I think just came out. This is only 2015. We have now a measure of the heat that's going into the deeper ocean. And what's the answer? That's where the heat went. Heat coming on the Earth, about the same if you average over solar oscillations. Surface temperature, sea surface temperature, roughly constant. The heat went into the deeper oceans. They did not predict how much it would go in. That we do not understand. The climate models are working on it. But the point is, energy is conserved. That's the most important part. The greenhouse gas effect is real, and that's where the energy is going. Eventually, it's going to have to heat up those oceans. Another question, are the glaciers melting? Is the sea level rising? This is a very short answer, and yes. How do you know? Well, you can take anecdotal evidence. If you go to Alaska Muir Glacier and take a picture of it in August 1941, you find this beautiful, beautiful glacier, maybe comparable to some of the glaciers in the Andes, maybe not, but beautiful. You go in August 2004, you see a very different picture. You might say this is even more beautiful, maybe not. The point here is glaciers are melting, but there's much better evidence. And there is evidence based on satellites. If the local acceleration due to gravity wobbles, it can be measured exquisitely by a satellite, in this case a satellite pair, and you also can measure the heights of the ice or land or sea level with this pair. And what do they see? Well, over this period, for example, from 2002 to 2012, they see that Greenland's ice is losing. Greenland is losing its ice. If there's red, it's gaining. If it's green, it's neutral. And if it's blue and magenta, it's losing it. So we're losing ice in Greenland. Even more scary, we're losing ice in Antarctica. And some of us were in Antarctica. We're close to here where we didn't see this. Well, it's not losing very quickly, maybe 5 centimeters of thickness per year, which doesn't sound like a lot. But here is the big fear of Antarctica, West Antarctica. There's a fear that that west shelf begins to collapse. And once it starts collapsing, it goes through its pace, enters into an irreversible mode unless the planet cools down again. And so here's the big fear. We don't know where this will end. It's not going to end 100 years from now. It's not going to end 200 or 300 years from now. How do we know this? We think we know this for the following reason. If you look 129 to 116,000 years ago, the last warm period of the Earth, it was only on average 1 to 2 degrees warmer. Remember the Paris Agreement to stay below 2 and to try to aim for 1.5 degrees. The sea level at that period of time, with 95% confidence level, was greater than 6.5 meters. Not a half a meter, which is what IPCC tells us will stay below in this century. 6.5 meters is serious. That's a 95% confident level. It's going to be less than 10 meters, but it's probably going to be over 7 or 8 meters. Okay. At 6 degrees centigrade, doesn't sound like much. Antarctica, Greenland completely melted. We're now talking 70 meters increase. Okay. Now, there are limits to adaptation when you're talking about 8 meters of sea level rise. This is in New Orleans, Hurricane Katrina. The movie star Brad Pitt was very moved by that. He started a foundation to rebuild correctly. It was Make It Right Foundation. And so here's a new house in the 9th Ward being raised on stilts, maybe 2 meters. The United States is spending about $8 billion to make a seawall to protect us for another meter. $8 billion. Okay? So 10 meters, different story. Let me change gears and talk about something else that you might think has nothing to do with climate change. This is cigarette smoking. History of cigarette smoking in the United States, 1900 to 2005. That black curve is the cigarette consumption of male adults over those years, and you see it rising, 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 peaking in the middle 1960s to the point where, on average, 225 packs of cigarettes per year, including the non-smokers. We are a very smoking country. A large fraction of the people were smoking, and they were smoking roughly a pack a day, kind of like what China is today. The blue curve, deaths due to lung cancer. When you start smoking, on average, it takes 25 years. Some people never get lung cancer. They never get emphysema. They never get all of those issues, health issues. But a lot of people do. How many? We now know today that if you smoke about a pack a day, you have a 25 times higher chance of getting, and it's mostly fatal, getting lung cancer. There's a 2 to 4 times higher chance of getting coronary heart disease, 2 to 4 times higher chance of getting stroke. This is the single most preventable health risk in the United States today, bar none. All right, what does this have to do with climate change? Well, remember that 25-year delay? Well, there may be a 50-year delay. Many climate scientists, you were being conservative, Rick. Many scientists think it's 100 to maybe 200-year delay. Why? The bottoms of the oceans are cold. It takes that long to heat them up. All right, so that's problem number one. Problem number two, once you get that carbon dioxide into the atmosphere, and you stop emitting carbon, does the Earth fix itself, and how fast? Well, we don't know whether the Earth will fix itself, but if things don't go beyond tipping points, estimated to be a millennia or so. This is a secondary smoke issue. At least 100 years, probably thousands of years. So here we are. I love to smoke cigarettes. It makes me relax. It's my own personal choice. What's the problem? I'll take the risk. Oh, my great-great-grandchildren will die? What's the problem? That is the attitude of much of society today. There is no problem. I don't want to change my habits for great-great-grandchildren. I will never know. And there's a small chance it might not be true. So what are the costs of climate change? I think Rick talked a lot about it. The climate refugees, the collapse of local agriculture, the rise in sea levels, 160 million people in Bangladesh, 6.5 meters will create about 40 million refugees, climate refugees. There's lowlands and there's mountains in Bangladesh. I talked to the ministers in India. They are scared to death over the last half dozen years that 20 or 30 million people from Bangladesh will swarm into India but have nowhere else to go. All right, so we're talking 20 times more than the Syrian refugees. 20 times more. Okay, so I think we have a problem today. We may have a very big problem. And these future risks have very large uncertainties. I'm not going to say this is exactly going to happen, that's exactly going to happen. We frankly don't know. But the more we know, the risks are going to 3 choices: bad, very bad, or catastrophic. It's kind of like cigarette smoking. All right, how much carbon should we emit to stay below 2 degrees? Well, IPCC and the Paris Convention was very clear. This is 3.7 trillion tons of carbon dioxide, or to put it in all forms of carbon, methane, carbon dioxide, didn't just support carbon. It comes out to roughly an even trillion tons. Except we've used more than half of it up since the beginning of the Industrial Revolution. So you say, oh, that's pretty good. At the beginning of the Industrial Revolution to now, we'll have an equal amount of time. That was about, 150 years, 200 years? No. The rate we're doing today, we have 30 more years to use the rest up. Okay? Time is running out. Carbon emission is the privilege, or that's sarcastically privilege, of emitting carbon at the rate we are. We have 30 more years, and the probability of going above 2 degrees is 50% or more. I see this as an issue that science and technology and policy really have to come to the aid. Energy efficiency, clean energy sources. But I also want to remind you of what Sheikh Yamani, the former Saudi oil minister, said. And he said, the Stone Age came to an end, and not for lack of stones. And the oil age will end, but not for lack of oil. Now, that is not why he's the former Saudi oil minister. What he was really thinking is, in order to get out of the Stone Age into a new age, a metal age, you transition to a better solution. Once we started using metal, we don't look at all the rocks in the ground and said, stranded assets. We don't see rocks today and say, shouldn't those be arrowheads and blades and plows? Okay, we have metal, better. But there's something he didn't say that was implicit. If you don't find a better solution, which includes an economically better solution, the oil and gas and coal will be used. Certainly the oil and gas will be used. So I'm going to ask you a question. I'm a professor. I give quizzes. It's a surprise quiz. When will the cost of wind and solar power become lower than the cost of a new coal plant or a new natural gas plant. For all those who believe not in the next 50 years, please raise your hands. For all of you who believe not in the next 20 years, raise your hands. For all those who are behind in the translation, raise your hands. And C, it depends. Raise your hands. Okay. It depends. Let's talk about where the prices are today and where they're going. Wind resources in the United States are remarkable. Those brown and yellow colors show that there are extraordinary wind reserves in the United States. The great news is it's over very inexpensive land, not many people, and so it's very cheap. And in the past decades, from 1980 to 2015, the cost of wind has plunged. In fact, the cost of wind in those middle states, new contracts being signed today, which includes the profit of the people who put up the wind turbines, is about half the cost of new natural gas if gas costs $4 a million BTU. I don't know how much it costs in Chile, but in Europe, maybe $12, $15 a million BTU, 3 or 4 times as much. Asia is even higher. So even though the United States has some of the cheapest natural gas in the world at that price, it's still lower in those good Midwestern states. So that's good news. Better news, we're not at the end of the technology line. The wind turbines are getting taller, the blades are capturing more energy, and they're getting much more reliable. So it is fully expected, just by gradual engineering, that the cost will drop by another 30%. Very, very good news. What about solar? Over a period of time, from 1978 to 2014, the price has dropped. Well, how much has it dropped? It's dropped more than 100-fold, because this is a logarithmic curve. And let me explain what an experience curve is. In every technology, if you double the deployment of a technology, the cost goes down by a certain fraction. You double again, it goes down by another fraction. You double again, it goes down by another fraction. And so this constant improvement and lowering the cost in automobiles, in wind turbines, in solar turbines, in computers, chips, in all these things, everyone follows their own experience curve. This happens to be one for solar. It just so happens that there was a little bump in 2008, so it went off the experience curve, it went below the experience curve, but the trend is it's going to go back to this experience curve. Now you can say, well, that's great. Let's wait a little while for it to get a lot cheaper, and then we can deploy it. There's a problem. The only reason the cost goes down is because there is some demand to actually make more stuff. If there's no demand to make more stuff, the price kind of stops. Okay, so that's one of the things in policy that people have understood for decades, but other people say, no, it's too expensive now. Let's not do anything. Let's wait for the cost to come down, except it won't come down if you don't have a demand for it. But not only are solar modules coming down, the real cost, the full cost has come down. And this is the record in the United States. And over a period of only 7 years, from 2008 to 2015, the cost went from roughly $20, 20 cents a kilowatt hour, $20 a megawatt hour, to less than 5. Remember, new natural gas, 5. So this is in Southern California, Arizona, New Mexico, Nevada, Texas. So in the sunniest parts of the United States, solar is also cheaper than new natural gas. Today, by 2020, we want 32% renewable energy, hydro, wind, solar, 32%, roughly one-third. The governor's asked goal by 2030, which is not too far away, California, he wants California to be 50%. But the 32% is written into our law. So it's a serious commitment, and we're marching there, and we will get to that. Solar is pretty good around the world. Wherever you see yellow and brown, it's very, very good. Where you see green, it's not good. Look at one hot spot down there, where you guys live, Chile. It's one of the best. So there's a new project being built by a company called Valhalla. And what they're doing is they're building a solar plant. The solar plant is going to be fairly big, 600 megawatt capacity. But sometimes you don't want the electricity when the sun's shining. You want it not at noon, but you maybe want it at when you eat dinner at 10 p.m., right? And so what are you going to do? The sun's coming down by 10 p.m. So you need to store energy. So what these folks have done is they're saying, oh, there's a high cliff near the ocean. When the sun is shining, we can pump water from the ocean to a little pond up high and store the energy. And when you need it, you let it come back down into the ocean. And so you have this combination of energy storage, huge amounts of energy storage, 300 megawatts of power, and solar that can supply a lot of power. So this project has started. It's being built in Chile. It's very innovative. I hope it goes very well because it will be a precursor to a lot of things in the future. What have I told you? I've told you renewable energy is going to be very inexpensive in good places. You do not want to put solar panels in London. With all due respect, it drizzles. And actually, in northern Germany also. You just don't want to put them there. In the best places, which are, that huge map is two-thirds of the world are best places, you can put solar panels and wind in a lot of places. Cost of energy is going to be very, very low, almost guaranteed 3 cents a kilowatt hour by 2020 in the best places, because we're already seeing this in the United States today. 2 cents a kilowatt hour probably by 2030, maybe 2035. Okay, so one problem. As you go from 15% renewable energy to 50% renewable energy, you have to have more backup power. You have to have a more sophisticated transmission and distribution system because you're generating intermittent electricity, and the wind stops blowing, when the sun stops shining, you've got to automatically turn on something else because you don't want a blackout. So that whole system cost and energy storage, like pump storage, is part of the cost of renewable. But 20 years from today, it will be so cheap, the total cost will be comparable, I think, if you do it right. And doing it right is very important. There are 101 ways to do things wrong, and there may be 2 or 3 ways to do it right. Long-distance transmission is a very big deal. China is the leading country in long-distance transmission because they have great hydro, wind, and solar resources in the western part of China, where there are very few people. But most of the people live in the eastern seaboard or close to there. So they're installing humongous transmission and distribution lines that are extremely efficient. 5 days ago, I was in China for 2 days, and I spent 4 hours with the State Grid. This is the big state-owned transmission distribution company in China, and spent 3 of those hours with the chairman of that grid. And China has installed over 60 gigawatts of plus or minus 800 kilovolt lines. That's the highest in the world, AC lines. And by 2017, they will have installed another 60 gigawatts, and by 2020, another 200 gigawatts. And during the dinner, Chairman Liu told me that they've just announced the day before that they will be installing a 1.1 megavolt DC line that will carry electricity 3,200 kilometers, and it will lose less than 5% of the energy in the whole line. Now, let's compare this to the United States. The vast majority of our lines, 95%, maybe higher, are below 500 kilovolts AC. If you use the most efficient of those lines and said how much power would you lose if you transmit 3,000 kilometers, you lose 85% of the power. So I think we are behind. Now, why are we willing to put up with that inefficiency? It's simple. We don't transmit 2,000, 3,000 kilometers. Even though the wind and the solar are best where there are no people. And there is a resistance, a political resistance to do this, but this has to change. Let me talk about energy storage. Here's the first form of energy storage. Wait, that's a windmill. That's not energy storage. That's energy storage. When the wind blows, you pump water from a well up to the surface. That takes energy. When you need the water, you open a valve. It takes very little energy. So when the wind blows, you use it to do the work you need, and then you have it ready to use. So we forgot about this over the period of 150 years. because electricity became cheap, abundant, and convenient. We have to start thinking about this again. Battery storage, well, Tesla is a beautiful car, but it costs over $100,000 for the long-range one. And the battery cost about $30,000 just for the battery. Now, most people don't want to spend $30,000 for the entire car. So what would it take to get mass numbers of people without subsidy to buy an electric vehicle? Well, you want to go 300 miles, 500 kilometers or so. You want to charge in 5 or 10 minutes for at least 100 kilometers, and you want the cost to be one-third. At that point, a $20,000, $25,000 car here's the technical term physicists use, the battery lasts longer than the bladder. I hope you translate that right. So you pull up, and while you're discharging, your car is charging, okay? And can you recharge for 200 miles in 5 or 10 minutes? At that time, game over. This is great. So I'm spending a little bit of my time working with Yi Shui, a professor in material science, trying to build a better battery. We may or may not, but what we're shooting for is the last one, lithium metal and sulfur batteries. We think if we get that chemistry rechargeable, reliable, durable, cheap, increase the energy density fivefold, the weight would be 4 or 5 times less. We have this world of cheaper energy. We have additional transportation distribution costs. But here's the only way I think we can go to 100% renewables. Beyond 50, 60%, because of the backup systems, and the batteries will be cheaper. They'll be 3 times cheaper, maybe in 15, 20 years. They still can't do summer-winter storage. They still can't do long distance. And so the way to do this is to take water, find an electrochemical efficient method and inexpensive, use that cheap electricity to make hydrogen from water. You take that hydrogen, and then the rest is known chemically. You can make CO and H2O, and from CO and more hydrogen, you can make methane gas, which you can power your fuel stations, or you can actually burn the CO and the hydrogen directly, known technology. Okay? But here's the best technology. You want to take water and carbon dioxide from steel plants, cement plants, the remaining fossil plants, even from the air. With that carbon dioxide, with that hydrogen, you want to make a liquid hydrocarbon fuel. You start with methanol, but you can work up your way. But methanol is pretty good. But you can work your way up to gasoline and diesel. Why do you want to do that? Because the transmission line becomes a tanker. We ship oil anywhere around the world for about $1 a barrel. Methanol is a little lower density, so it's $2 a barrel. You can put it on your country in big storage tanks, and so you have energy security for half a year. This is what we do with oil today in the developed countries. So you have energy security, you have energy transmission, you have energy on demand. This is physics and chemistry. And so here's the moral of the story. In order to get true sustainability, you have to recycle carbon dioxide and use it over and over again in some carbon fuel. And then you take the carbon dioxide and recycle it. And what does it need? It needs cheap energy, which makes hydrogen, and cheap energy that grabs CO2. And so this is the challenge. Any chemists and physicists out there, you solve this one, you've really saved the world. So let me conclude with another picture of the pale blue dot. This particular picture was taken in the Apollo mission in Christmas Eve, 1968. In the last of the orbits, the astronauts turned the capsule, looked earthbound, and one of the astronauts took this picture. And he said, "We came all this way to explore the moon, and the most important thing is we discovered the Earth." Look at that picture. Do you want to live on the moon? It's pretty bleak. There's no air. There's no water. Not a good place. Look at that Earth. From that vantage point, it looks pretty good. From the vantage point inside the island, Chile looks pretty good. Look around. Nowhere else to go. I think we have a moral responsibility to the most innocent victims of climate change. They're the poorest people in the world who really don't have the financial resources to adapt. They will suffer. Many will die. And the children and grandchildren, the great-grandchildren, and 1,000 years beyond of secondary smoke, those people will also suffer. And they are truly innocent. They're not going to be born for 500 or 1,000 years. And so there's an ancient Native American saying which says, we do not inherit the land from our ancestors. We borrow it from our children. Thank you.
¿El futuro? Despierta. Bienvenido al Congreso Futuro. Despierta, conéctate, participa.